Sorry about that. The recording time just kind of ended before I realized what was happening. So next we have we successfully cloned this ball into two balls. Hooray! But maybe we didn't. As in most paradoxes, there's at least one assumption made that were it false, it would be impossible. In this case, I am referring to when we mentioned something that we'd have to worry about later, a little while ago. But what exactly did we do that may have broken a rule? Is it the part where we defined the sphere as an uncountably infinite number of countably infinite sets? Which is no, we're allowed to do that just fine. The sphere originally was an uncountably infinite number of points, but we counted it as an uncountably infinite number of countably infinite sets. But those are both the same size. We're allowed to do that. The only legitimately questionable part about the paradox was the part where we assumed we could pick one element from every one of our mini hyperwebsters. Like, we composed this of an uncountably infinite amount of calligraphs, little mini hyperwebsters, and then we just, in order to name every point in the sphere, we picked one from every hyperwebster. To do this, we have to assume something called the axiom of choice is true. The axioms of choice is the ninth of 9 axioms of mathematics in the system known as Zermelo-Fraenkel theory, or Zermelo-Fraenkel set theory, and it's the only axiom in the theory that isn't universally accepted as true. In its simplest form, it states that if S is a collection of non-empty sets, like here I have S is a collection of the natural numbers, the whole numbers, and integers. Then we can create, its axiom says we can create a new set of elements called a choice set, which can be formed by choosing one element from each set in the collection. Meaning, so here I chose 1 from the natural numbers, I chose 0 from the whole numbers, and I chose -2 from the integers to create this new one. This claims to be true regardless of the size of S and regardless of the size of sets in S. In other words, even if S is uncountably infinitely large, like say if this was there were uncountably infinite amount of these things, and each of these things represented a calligraph, we would still be able to create a choice set from that. Common sense wise, this makes sense. So, like, we defined each calligraph had all those points in it. So we know each calligraph has points in it, so we're allowed to pick a point from every mini hyperwebster, from every calligraph. But there's no way to prove it because there's no systematic way to check every entry in an uncountably infinite set to make sure of it. There are so many calligraphs, there's no way to go through all of them and make sure we can pick a point from each one. So as we showed, the concepts of infinity do allow us to pull some ludicrously fun and weird proofs, but in this case, the axiom of choice is the one place where the notion of infinity hinders us by getting in the way of itself. Where infinity is so large, we can't not only we can't comprehend it, which is normal, but we also can't even systematically comprehend it or mathematically comprehend it. There's no way to determine what it is. And yeah, here's the bibliography. Thank y'all for watching. Professor Douglas Ward. Hope you liked reading my paper originally. If for some reason there's somebody is watching this on YouTube and could make it through the whole thing, I'll include my paper in the description below so you can actually read through this stuff instead of hearing me talk about it. It'll make a bit more sense that way. I can say all the research on this, most of it was done through the P and the Sun, a mathematical paradox. This book here, I wouldn't have been able to understand any of this if I hadn't read that book. So that was great, and I hope y'all have a swell day, have a wonderful life, and that was the Banach-Tarski paradox.